This video is going to discuss the derivatives of logarithmic functions. Before beginning, I strongly encourage you to take some time and review log properties. And for example, what I mean by this is if you have the logarithm, so I'm just going to do log base 10, log of x times y, that is the same as log of x or plus the log of y. These are going to come in very, very useful, both in this video and in your studies in this topic. Okay. The other things that I want to remind you of are that, so the graph of e to the x looks, the natural exponential function looks like this, and the natural log of x is its inverse function, so it's symmetric about the line y is equal to x. So in case we ever have any graphing problems that we're going to run into, we're able to answer those questions. And then this is the last relationship because of that inverse property. Okay. Now, when we look at the derivatives, we're going to take these at face value right now. If you want to know their exact derivation, they are in many calculus textbooks, using, again, the basic definition of a derivative. Okay, so we say that the derivative of natural log of x, and we have absolute values here just so that we don't run into any domain issues. So the only value we're excluding from the domain is 0, at least in this basic function. Also, just a reminder, for natural log of x, if we don't have the absolute values, we have to have the input, which is x in this case, to be positive. Okay, so if we're ever asked for domain issues, that's when we have to set up an inequality and solve. So the derivative of natural log is just 1 over the input times the derivative of the input. And that's in the case of natural log. In the case where we have log base a, where the base is not e, we just have to include a natural log of a term in the denominator. Okay, so in general, these are, again, the general definitions that I stick to. If we look at the derivative of the natural log of a function, it's 1 over that function times the derivative of this function using the chain rule. Same thing for natural log of log of base a. Same sort of thing. The only thing that's different is we have a natural log of a in the denominator. Okay, so let's go through some examples. So we want to differentiate each of these. So there should be a comma in there. So the function is natural log of the absolute value of that, and we're restricted to the domain. We're restricted to the domain where x is less than 4. That's just a technicality. It's going to work out in we're going to differentiate assuming that we are inside the domain. Okay, so if I want to find the derivative of f of x, so f prime of x using prime notation, which again this would be, not this, but rather I could also write it as df dx, same thing. This is equal to 1 over the input of the natural log, so it'd be 3 minus x cubed plus 1, and then I would need to multiply by the derivative of this function. So the derivative is going to be, well, chain rule for this first part, 3 parentheses 3 minus x squared. Okay, and then I have a derivative, so that's the derivative of the outer part times the derivative of the inner, which is times minus 1. And then the derivative of the plus 1, which is a constant, is 0. Okay, so that would be the complete derivative for this function. Okay, so just to review, 1 over the input for a natural log, and then times the derivative of the input. Okay, which in this case had a chain, and it was a 2-stage chain. Okay, so we're done with that problem. Now on to g. So g of t looks very complicated, but now here, this is exactly why I want you to take some time and review those log properties, because we can use the algebra, or those properties that we get from logs, to simplify this. Okay, using the power law of logs, I can write this first. I am not differentiating. This is still just g of t. This is equal to 2 times log base 2 of 3 minus t over t squared plus 1. Okay, and Well, okay, I still don't know how yet to do a derivative of a quotient, because I can do, okay, 1 over this, and then take the derivative of the inside part. I don't know how to do that right now. So I'm going to keep breaking it up, remembering that if I have, so this is still g of t, I haven't differentiated. If I have the logarithm of a quotient, that is a difference of logs. So log base 2 of 3 minus t minus log base 2 of t squared plus 1. Okay, and just for my own peace of mind, I'm going to distribute the 2 so I don't forget about it. So I'm going to write this as 2 log base 2 of 3 minus t minus 2 log base 2 of t squared plus 1. And now this is much easier for me to differentiate. So again, try to do some algebra before you actually differentiate. And now I'm ready to differentiate, so dg dt, or again, this is, I could write it as g prime of t. This is, okay, the constant is going to stay there, and I take the derivative of the log, so that's 1 over the input, times the derivative of the input, which is just minus 1, minus 2 times, and then 1 over the input. Oops, and I forgot something. I'll go back and fix it. T squared plus 1 times the derivative of the input to t. And I forgot here that this should be times the natural log of the base, so log base 2, in both cases. Okay, so rewriting this now, I would have negative 2, I just multiply all across, over natural log of 2 times 3 minus t. Make sure to have parentheses in the denominator. Minus, and then multiplying across, minus 4t, which I could, or sorry, it would be positive 4t. So it would be 4t all over t squared plus 1 times the quantity natural log of 2. Okay, and that would be my derivative. So again, dg dt, which is equal to g prime of t. And that would be my final answer. Okay, just to review, what I did first before I differentiated was I tried to simplify this down some using the algebra of logs, or those log properties, log laws, whatever you call them. Okay, bring the power down in front. Okay, great. Then I broke the quotient up as a difference of logs and distributed the coefficient. Then I found the derivative, remembering at the end that I needed to have a natural log of 2 in there, and then I just simplified it. Okay.